Okay, so my name is Selina, and I will be the presenter today because Carlos, our community leader, is sick. He's with us here, but he is avoiding to put on his microphone and his camera. So I will speak today. We have Saurav with us, and we're learning something about benchmarking self-supervised learning methods today. And I will give a short introduction about the community, and then he will give us some content about this topic. So first of all, we are recording this. And second of all, you can ask questions whenever you want. We have a Q&A session here, and we have a chat here. So maybe you can ask questions, and then we can interrupt Saurav in his talking, and then or we can have a Q&A session later after his presentation. So who are we? What is the Gen AI Gurus community? We were established in June 2023. We're almost having about 400 members on Meetup. We're an open community for newcomers and experts. And our goal is to have a guided learning from basics to advanced hands-on concepts. First of all, I want to talk about our upcoming expert talks. We are hearing something from Andreas in the beginning of October about latent generative modeling for efficient visual synthesis. And in the end of October, we will hear something from Duigu. I hope this is pronounced right, about exploring audio LM, a bit of paper dissect, a bit of code. So who are the community leads? I already mentioned Carlos, who is with us today but sick. He's a software development manager, data-centric at Bosch. I'm Selina. I'm working in global advisory in the field of risk management for generative AI. And then there's Gerd, who can't be with us today, and he's a CTO in Berlin, Germany for Cloud Ace. So today we have Saurav with us. He's a machine learning engineer at Recourse AI and based in Manchester. He's a Google developer expert in machine learning. He conducts research on geometric deep learning and representation learning at the University of Manchester, and he's passionate about open source. And then Saurav, you can maybe tell something about yourself if you want to add something, or you can start directly.
Hello, everyone. Thank you for joining. Let me get to my slides again. Can we see my slides? Selina, if you could confirm.
Perfectly.
Lovely. Lovely. Okay, so today we'll be talking about self-supervised learning methods. Depending on how many people have heard the talk, you can either be very enthusiastic at the moment or very surprised as to why we should care about this at all. Hopefully by the end of the talk, I can motivate you to pay some more attention to the recent papers coming out in this field. So again, as Selina said, hi everyone, I'm Saurav. I'm currently based out in Manchester. I'm a research machine learning engineer by trade. I do overall work in either geometric learning or representation learning. I also do a lot of open source work, so you can often see me committing to either Hugging Face or Python Geometric. I also like coffee a lot, and I also watch sports a lot. So I support Mercedes and Manchester City. Again, if you want to talk about sports offline, more than happy to do so. But yes, so overall, the outline of the talk, I'll do a very gradual introduction to what self-supervised learning is. Where did the field start from, and we'll broadly go over the various families which exist in self-supervised learning. We'll cover 4 to 5 methods in total, one of each category. We'll talk about the various similarities and differences within the various families itself, and then I'll give you links to resources about where you can read more about it, read the code in whatever language or library you like, and towards the end we'll do a small Q&A session if people have any questions. And all the code used for the various models is available on my repository called Self Supervised Learning. I also have lots of open issues there. So if people want to contribute and are interested in implementing various methods, feel free to assign yourself a issue and we can work offline. As a side note, almost most of this talk is inspired by this recent paper by Meta and other collaborators called A Cookbook of Self-Supervised Learning. I would highly recommend for anyone who is interested in the field to go through this paper. It contains theoretical side notes, implementation details, hints as to why certain hyperparameter works and why certain other ranges do not. It also covers some theoretical aspects of it. So you should definitely read this paper if you're interested. And on the left, we can see a very cute photo of a dog which is holding his or her own leash. And that is, in fact, what self-supervised learning is about. So again, another blog post which maybe people should read is called Self-Supervised Learning, the Dark Matter of Intelligence. It's written by Jan LeCun and Ishan Misra. But I really like this quote a lot because it really sums up what we're trying to do in self-supervised learning. And that is to build background knowledge and approximate some form of common sense. Right. So if we do supervised learning, for instance, almost every time we're training for a particular task, right? You're either training to classify images or detect bounding boxes. We're not actually trying to learn, I know, some inherent features or representations about what the data means. However, in self-supervised learning, what we're trying to do is just learn representations from whatever information we have. We're not training for a particular task. We can, of course, fine-tune a classifier for tasks, but our main job here is to just learn as much as we can and hopefully gain some overall knowledge about what our data tells us to do. Again, why should you care about self-supervised learning, if at all? The simple answer is supervised learning can't take you everywhere. Data annotation is expensive. So while supervised learning is limited by labeled information, it is also enabled by it, of course. That's why we have giants like Google and Meta who train lots of models using supervised learning and deploy it in various scenarios. But then again, for smaller companies, if you don't have tons of compute to train your model, self-supervised learning can be a very interesting approach to take. Self-supervised learning in particular works with unlabeled data sets, so we don't need to do much work, right? We don't need to have annotators who label our data. You don't need to go to Mechanical Turk and pay tens of millions of dollars to annotate whatever data sets you have. If you just have data, you can work with it. And in fact, I think this is one of the most ignored aspects of sort of large language models in general. But it's the fact that large language models are inherently based on self-supervised learning. Right. Most large language models are trained using something called master language modeling. It's something which we'll cover later on in the talk. But then again, self-supervised learning is the reason that most transformers are as good as they are. It's because they're trained to just understand the language and then people fine-tune it for various tasks. So overall, the objective of self-supervised learning in a more rigorous fashion is to learn to restore missing or distorted parts of the input. So that's one aspect which we could look at. Or you could also contrast two views of the same input. What I mean by that, we'll cover some after some slides. But then again, the entire objective could be reduced down to like these particular aspects, which is some sort of restoration or some sort of contrastive means of learning. One particular area where supervised learning could be helpful is where labels are very costly. So again, labeling images is particularly simple, but if you have medical data sets, for instance, annotation can be very expensive because you need to hire very knowledgeable healthcare workers. So labeling medical data sets could be particularly expensive, and there are a lot of success stories out there which tell why self-supervised learning works especially well in regimes like that. Also, they work where you don't know the task beforehand, right? If what you're trying to do cannot be simply expressed using a task or a metric, then maybe self-supervised learning is what you should look at. Overall, the workflow of self-supervised learning can be sort of separated into these 4 chunks. We will mostly focus on the middle 2 bits, which is having an augmented data set and then training a self-supervised learning model. But overall, the workflow looks like this. So your first step is, of course, to get the data set. It's unlabeled, so just simply getting it works fine. Then the second step is where we augment our information using some way, shape, form, or manner. Now, this is the important bit which sort of separates unsupervised learning and self-supervised learning. Unsupervised learning is completely devoid of human inductive biases, right? We're not telling the model, hey, you should focus on this, or this sort of geometry or symmetry in our information is very important. Self-supervised learning, on the other hand, while it has no supervisory signals, we do provide some sort of a bias by augmenting it in a said way. How we augment depends on the modality. We will cover some examples, but we should particularly focus on the fact that it is at this stage that we introduce some human biases. The next step would be to actually train the model using some self-supervised learning objective. And again, from this last few slides, we should remember that there are sort of 2 ways which we could take. It's a restoration of some form or a contrastive learning of some form. Right. The last step is actually how you get self-supervised learning models to work, and that is to either train a classifier on top of it for a particular task, not a classifier, like whatever task we want, but that is how you evaluate sort of self-supervised learning models. But in most of our talk, we'll focus on the center 2 bits, as that is the most interesting bit. The last 2 bits could be covered more in data engineering or evaluating models per se. Now, let's actually get started and talk about what the various self-supervised learning methods are. This figure, again, this is from the blog that I talked about by Lacoon and Misra, but this is what we're trying to do here. So if we imagine our information to be like a cuboid. So what we're trying to do is we'll distort some of our information. We'll remove chunks of it. So as you can see in the first row, we have just like removed the last few bits of it. In the second row, we have taken out chunks from the middle. And in the third rows, we have not removed like equal things, but we have like, the last row, the most leftmost element is a way smaller cuboid than what the others are, right? So you can distort your information using various ways. Now, the first paper that I would like to talk about is a simple framework for contrastive learning of visual representations. I prefer its acronym instead, SIMCLR, SIMCLR. It's a paper which came out of Google Research. Ting Chen, Simon Kornbluth, Mohammed Norouzi, and Geoffrey Hinton. Now, we'll spend a lot of time on this particular paper because I'll also introduce some terminology like views expander encoder, but we'll go over the other few papers relatively quickly. Now, okay, so again, as I said, I like coffee a lot, so you'll see coffee pop up in various slides. Now, Simclar, for instance, worked with with images. So assume you have an image. On the left-hand side, we have a beautiful animation of a coffee mug. Let's call it X, right? And what we do is that we make two views of the same image, right? So we have one image and we are creating two views from it. How we create the views? Now, this is where augmentation comes in. So we augment the image in some form. As you can see in the top row, we have just shifted the image to the top left. And in the bottom row, we have changed the color scheme, right? So it inherently represents the same information, but it's a different image. We call these things views. And this approach is contrastive in nature. So we have X's and we create some sort of views, X tildes, and then we encode the image into intermediate representations. So the encoder is what you can see as F in the image for most visual tasks. Encoders are usually a pre-trained ResNet backbone. Some people even use VGGs, but those depend from task to task. Most people recommend using ResNet. So you take one image, create multiple views. Right now we see two views, but you can create as many views as you want. So you create multiple views of the same image, you encode them into intermediate representations, and then we expand them. The G is called the expander. It's for most cases, it's a very small MLP. So imagine like a 3-layered 128 neuron simple MLP network. It's called the expander. The expander is of key importance as we will explore later on in the slides. And then we have these things called they are called either the latents or the codes. I like the word codes instance, so we will refer to these as codes, and these are ZIs and ZJs. Right, so we have essentially gone from one image, we have created multiple views, and then we have certain codes corresponding to each view. Now, as you can see, ZI and ZJ inherently come from the same image. Therefore, in whatever representation space there are, they should lie relatively together, right? Because those two codes correspond to the same object, which is like a coffee cup. Now, that is the task which we're trying to do here. So we're trying to sort of cluster together representations from the same image. So you create multiple views and you want similar views to stay together. Now, of course, our data set will not just have coffee mugs. It will also have, for instance, I know, a goat, right? So you want the representations of coffee cups to be together, but very far away from what a goat is, right? But of course, goat should be relatively closer to, let's say, a horse, right? So we have sort of this contrastive training paradigm where we want sort of these positive views, positive meaning they belong from the same parent image, to be together, but be as far away from negative views as possible. Now, this relatively simple training paradigm leads to particularly surprisingly well results. Also, as we will explore later on in other methods, this sort of simple contrastive training paradigm also leads to some surprising hidden qualities which just naturally emerge. Again, to summarize, you have images, you create views, you encode them, you get intermediate representations, and then you have corresponding codes. Codes from the same image are called positive views because they belong to the same class, and then you also have negative views, which is everything which does not belong from the same class. And then again, there are a lot of parameters you can control here. How many views do you want? What are the different transformations which you want to do? What is the output dimension of the codes? What is the output dimension of the encoder? And then again, there are various hyperparameters which have been shown to work well. If you want to know what those are, you should again refer back to the original paper. Now, my slides will also have some amount of code in it. You should not focus on the actual code itself. I would rather show you like 3 to 4 different ways to achieve the same thing. So depending on how your current code base is structured, you can sort of pick and choose to whatever might best fit in your pipeline. In this particular example, we are creating a custom augmentation class. It's a simple Python object. So if you want to use this, you'll sort of create a class. You will define the various transformations which you have. So for instance, we randomly apply image flip left, right. So you randomly flip the image left to right, top to bottom. You can also change the inherent color scheme of the image. You can drop it. Drop meaning you can convert a colored image to a grayscale image. You can also jitter it, which is you increase the contrast, increase the saturation, increase the hue. Again, we're trying to distort the image as much as possible, but retain its original structural information. And then you can simply call this using like a data augmentation pipeline. Most of the code in my talk will be in either TensorFlow or Keras, but there are very easy PyTorch implementations available as well. If you are a Torch person, you can find corresponding PyTorch implementations on my repository. Now, moving ahead, let's look at like a sample training step. So the training step is relatively simple, and again, we'll spend some more time on this because I just want you to absorb the structure of it. Most training steps will look the same. So you create the codes itself. As you'll remember, in the image, they were called ZIs and ZJs. So you get some ZIs, which is, again, you pass the image through the model. In the next line, you can see we normalize the image. This is, again, this helps the model to train better. It makes it more stable. And then we sort of create negatives as well. So you will, of course, you'll have multiple views from the same image, and everything else is a negative view. So you collect the positive views together, you collect the negative views together. And then for every positive pair, you enforce that they are close together, and you enforce that the negative pairs are far apart. How do we do it? You can see in the code, we apply sort of a negative mask, and then we scale them using a temperature coefficient. Again, a key thing to notice is here is that we only loop through the positives, not the negatives. So we're training for the positive views to be as close as possible, thereby directly pushing the negatives as far away from each other as possible. Again, I try to notice and remember this. This structure will come up again in the other methods as well. Of course, a coffee break in the middle. Now, there are 3 particular resources which I would recommend you look at. First is a very nice, well-written, simpler example by Andras Perez. It's there on the keras.io example side. Very nice, concisely written. The augmentation pipeline that you saw me cover in the last slide was from his example. There's, of course, the official implementation from Google Research as well. And then SciPaul wrote a very nice minimal implementation in TensorFlow 2. So you can check out that as well. Next up, let's discuss another popular paper called DINO. It's titled Emerging Properties in Self-Supervised Vision Transformer. This paper came out of Meta Research. Again, popular authors include Mathilde, Caron, Hugo, and Ishan. Misra, you'll see these three people quite a bit in the self-supervised learning literature. I particularly like this paper a lot. It was my first proper introduction to what self-supervised learning is, and this is what sparked my interest in overall representation learning. Now, let's have a look through of what the method actually looks like. Now, as you can see, it looks relatively similar to what Simclar was. Is just sort of flipped upwards. Now, how it is inherently different is that we have, well, firstly, a teacher-student training paradigm. And secondly, we use something called a stop gradient, which sort of prevents gradient updates to the student, to the teacher network. And again, it's relatively the same thing. So you have an image, let's call it X. You create two views, X1 and X2. Then we encode them using a student, using any given encoder, usually, again, as I said, a ResNet. And then we just, instead of passing it through an expander, in DINO, you just use the output from the encoder itself. Now, there are certain engineering tricks which we apply. For instance, in one of the sort of the leaves here, we center the representations. So center meaning you just take the mean and then force the matrix values to be around that. And then we take the softmax of that. So again, using this, we're trying to, in literature, it's called soft classes or soft probabilities. And those are like P1 and P2. And this is actually what we use while training it. The key thing to notice, as I said, we have a student-teacher paradigm. So we only train one network, and the other network is just a moving average of the parameters of the other network. Why we do this? Well, it's a different training paradigm. The authors notice that there are significant improvements in the results. And also we have something called the stop gradient. Now, what that means is, while we're training, we only update the student network. Again, now this is just to ensure that the teacher network doesn't actually learn anything using whatever optimizer we are using. Its task is to just sort of replicate whatever this the other network is doing. Now, DINO was a particularly popular paper because it naturally allowed for the image representations to also learn segmentation masks. Again, it's a very simple paradigm, right? We're just trying to ensure that the positive views are relatively together and the negative views are relatively apart. However, it just naturally happens that the representations for images that we learn have segmentation masks inherently in them. Again, that is why it was relatively famous. There was also a version 2 which came out. Highly recommended to read both of them. Next up, so again, these are sort of some training runs on training a bunch of architectures on Cypher 10 using DINO. You can see I compare various optimizers, encoders, different seeds. All of this can be found in a blog post. I'll share the post in the later slides. Again, a very similar paper is exploring simple Siamese representation learning by Kaiming He and Jinli Chen. You might have heard of Kaiming He. He's responsible for the He initialization, which is, I think, the default in most libraries. I think it's only second to Xavier initialization. But then again, it looks very similar. right? So you have images, two views, you pass them through encoder. The only difference being is that now in one of the sides here, we also have an expander, or well, again, as I said, the various terms which are used for that particular smaller MLP, but it's inherently the same. So you get some sort of intermediate matrix which you pass through another simpler layer. And then again, we have the same tricks as DINO did. It was a very simple follow-up, but the authors essentially questioned if we actually needed the various engineering tricks which the author of DINO used. Right, and the result was, if you don't use centering, if you don't normalize, if you don't have the softmax layer, it actually doesn't matter. You'll get relatively similar representations. And they don't use a momentum encoder either, right? So we don't have like an exponential moving average here, and they don't use negative pairs as well. So it's a very minimal version of what DINO did. But then again, I think numerically speaking, DINO and SimSiam differed by 1 or 2% in whatever the metric was. Now let's walk through the training code. Before that, again, so earlier we saw like a Python object implementation of what a pipeline could look like. This is like a very simple functional view as well. So essentially what you do is you pass every image to this custom augment function, which does various augmentations. Again, it's not necessary to have a class. You can do it very simply within functions as well. A fun thing to see here is that we have a @tf.function decorator. So if you have a TensorFlow pipeline, this will immensely speed up this particular the augmentation bit of your pipeline. The training step, this for SimSiam, again, very simple because it's a very brought down version of what DINO is. But you have various Z's. So you have Z1 and Z2, which are the two views. And then you have the representations P1 and P2. You simply get a loss function, and then you do parameter updates. Again, very simple, but again, very nice results. So I wrote a blog post on DINO. It's up on weights and biases. That's where the particular plot was. I do lots of ablation studies as well. So if you want to see what optimizer works best, what parameter values work best and why, please read that blog. There is also a Keras.io example on SimSiam by Saikpal on Keras.io and a corresponding TensorFlow implementation on his own repository. Next up, so this is a very mathy title. I know VICReg, various invariance, covariance regularization for self-supervised learning by Lacoon and friends. But simply said, what we're trying to do here is making sure the representations that we get are inherently very similar. So not only are the two views close to each other, but the views itself are similar to itself, right? Now let's see what that actually means. Again, very similar to what SimCLAR did. In fact, it's exactly the same except the last step, minus the point that here our encoders have shared weights. So we essentially use the same encoder each time. So again, it's the same thing that we have seen so far, but let's focus on what the codes are, right? So you have two Z's, and what we're trying to do is that we are making sure that the two Z's are close to each other. So this is exactly what SimCLAR did. But what we also want is that the various dimensions within the codes, they are also similar to each other, right? So we want the covariance between the various dimensions to be the same. And we also want the variance between the various slices of the representations to be the same. Essentially, whatever the codes are, they should be similar and very close to themselves. Again, it's a very simple trick on top of SimCLAR, but they do achieve like very nice results. It's a very simple read what the paper does. You can inherently, if you don't have like a strong mathematical intuition as to what these various regularization tricks are, you can simply skim over the fact and just remember what we're trying to do here is ensure that everything just looks nice and simple and close to what they are. This is the third way in which you could sort of augment it, which is a functional view. And as we'll see, this functional view is then used within the training pipeline. So very simple to, again, similar to what we have seen so far. Whatever the train step you have. So this is the training step for VICReg. I know it looks kind of big. I'm not sure if the code is readable or not, but just hear me through it. So we get various image augmentation. So we get views, x1 and x prime. We pass them through an encoder. We get y and y dash. We pass them through an encoder. We get z and z dash. And then essentially we want z and z dash to be close to each other. We want the various aspects of z's to be close to each other. And then we also want the various dimensions of z's to be close to each other. So if we imagine z's to be like a three-dimensional matrix, we want it to be similar sort of lengthwise and also widthwise. And then we also want the two z's to be similar to each other. And then again, you get the variance loss, you get the covariance loss, you get the invariance loss. And then the total loss is a weighted average of these three said losses. And then you just do parameter update. Now, the official representation is on Facebook research's GitHub page, and I myself wrote a very minimal implementation on my own repository. If you want to have a read, please check it out. It contains both PyTorch and TensorFlow implementations. Now, lastly, this is perhaps where self-supervised learning really took off. It's in this paper called Masked Auto Encoders are Scalable Vision Learners. Now, again, work by Cumming, He, and friends. And it is essentially a direct translation of what we have learned in the NLP literature. So transformers are trained using something called the masked language modeling paradigm, right? So what we have is, for instance, we have a statement, Saurav likes to drink coffee, but you create various instances where you mask out the words. So it can be Saurav likes, and then it's a mask, drink coffee. What does the mask have to? And then we train the model to sort of fill in those words. We are essentially training a model to fill in the blanks. That is what transformers do, and they're very good at it, and therefore they have very good representations. So we take that bit of trick and then we directly apply it to vision as well. That's why like masked auto encoder. So we're trying to do some sort of masked modeling and applying into vision. And what we find is that that particular paradigm is really well scalable. Again, this looks very similar to, for instance, VIT, vision transformers. And it is arguably the same itself. So you have an image, you create patches. The only difference is you distort the image beforehand, right? And then you train the model to fill in those patches. So you have a model, you create patches, you pass it through an encoder, you pass it through a decoder. The decoder could be also understood as an expander here in order to sort of agree with our previous methods. And then you train the model to sort of fill the gaps, right? Again, very similar to what what vision transformers do, but again, it's very scalable compared to other methods like DINO and similar. This method perhaps scales the best when it comes to the dataset size. Now, this is the last way in which you could perhaps implement augmentations, which is you create what's called a custom layer. The PyTorch variant would be like a custom PyTorch module. We can see various implementations on my repository and across the various other official implementations as well. But what we essentially have is we create like a special layer, a special Keras layer in this instance to generate patches. And then we call this this particular layer within your normal Keras data augmentation pipeline. Again, it's just a special class which comes wrapped with helper methods, which Keras is nice enough to offer you. Now, there is an official implementation out there by Facebook Research. It's in Torch. So if you're a Torch person, look at that. There is also a very nice Keras example called Master Image Modeling with auto encoders by Oritra Roy and Soik Paul. Good friends of mine. I would highly recommend you to read through that example as well. It has a very nice flow to it, and it's very simple to read through. Now, this sort of wraps up the various 4 families that we have. So first up, we discussed what SimCla does, a very simple contrastive view. Then we have then we discussed DINO and SimSiam, which are sort of like they are the deep metric learning family. Then you have the very mathy paper called VICReg. Again, essentially same to SimCla, but you're trying to enforce similarity between the various codes as well. And then lastly, we discussed like essentially the transformer variant of self-supervised learning, which is masked auto encoders. Lastly, before finishing, here are some practical tips which I have discovered, and you can also read this in the cookbook paper. But one of the key points in self-supervised learning would be getting the augmented data set, and there are like lots of papers out there which tell you which particular augmentation you have to do. Another aspect which is perhaps less focused on is how you get the negative samples in the first place, and that is very important. If you do not have good negative samples within a particular batch, you are essentially training a deep neural network to do clustering. And we don't want to do unsupervised learning, we want to do self-supervised learning here. Now, theorists tell that most loss functions used in self-supervised learning, which is usually some variant of the contrastive loss, automatically handle sampling at the batch level. It's just how the loss functions are made. So you don't have to focus very much on sampling, thankfully, but you do need to make sure that you have large batch sizes. If you have large batch sizes, you automatically get very sort of quote unquote hard negative samples. What hard negative samples mean is that, for example, if your batch has a coffee mug and a bottle, right? So while a bottle is a negative sample, it is sort of semantically speaking in the same space. But if you have like a large enough batch size, it will put a coffee mug and a goat together, right? So if you have large batch sizes, you will automatically get sort of quote unquote hard negative sampling. But however, this is also like a limitation, because in order to have large batch sizes, you will need to have like large GPU memory. If you go over to my repository and see some of the runs for VICReg, you will see that VICReg works beautifully if you have batch sizes of 1024 or 4096. However, it fails terribly if you have 16 as the batch size, for instance, as you can see right here. So this is the loss function compared for, I think the bottom thing which you see there, and that is, by the way, at that point, the model learns to overfit. So in I think that's 13 training steps. If you have a large enough batch size, you can learn really well. I think this was Cypher 10 or Flowers. So 5 or 10 classes. However, if you have extremely low batch sizes, so at the top, I think that was a batch size of 16 or 32, you will just never learn, because it is essentially training to do clustering. However, the metric that it has is classification, so it will just not work. So try to have as big of a batch size as possible. Another one last final tip which you could do is have the so the intermediate MLP that we talked about, right? That plays a very key role. Theoretically speaking, theorists think that it prevents high dimensional collapse. So essentially, it ensures that the clusters are nice and wild in the representation space. Again, theorists think that. I don't think we have like a pure mathematical proof as of now. It also helps mitigate the noise of data augmentation. Noise of data augmentation meaning, like, obviously we destroy our data, right? However, we're trained to recover it. So recovered images, for instance, should not have much noise. So having like a large output dimensions, make sure that the noise is as low as possible. So Empirically speaking, meaning like if you notice and compare the results, having a large output size really helps a lot, especially in covariance-based methods. So, for instance, in VICReg, if you have a large outputs dimension, it works really well. Again, just to summarize, so we discussed what self-supervised learning is, why you should care about it. We discussed the various families of model. We introduced a little bit of terminology, so encoders, expanders, codes. But the key thing to remember here is we either train for like a restoration task or we train for a contrastive task. Both of these methods work really well. In fact, there is a Kaggle kernel out by a fellow colleague of mine, Ayush Thakur, which shows that if you pre-train a model using, I think he used SwAV. So if you pre-train a model using SwAV, the pre-trained weights are actually better than ImageNet weights for image classification. Right, so self-supervised learning in most cases beats supervised learning for downstream tasks. So if you're just interested in learning like a very good representation space, you should perhaps look into self-supervised learning. A lot of startups are now shifting from supervised learning to self-supervised learning paradigms for their own models. Most of NLP relies on self-supervised learning. So again, it's a very key factor to remember. It's often overlooked in text a lot, but now recently, because of retention networks coming out, I think if you try to translate some ideas from self-supervised learning, people will notice a lot of great performance boosts. So hopefully some of you like self-supervised learning and would like to pursue them more. If you want, again, a very good introduction is the cookbook paper by Meta AI, and then there is a very nicely written blog post called Self-Supervised Learning, the Dark Matter of Artificial Intelligence. Those are very good starting points. So if you want, please start from there. There is my repository, which contains implementations of these various methods. There is both like a Python script and notebooks. So if you like notebooks more, those are very minimal examples meant for like the free GPU, which you get. They are on very small data sets, but I also have implementations which are meant for scaling. If you want to implement more of these methods, I have open issues on my repository. So if you want to contribute, please go there. And again, always accepting contributions there. If you have questions, feel free to reach out offline as well. Now, perhaps we can open up the talk for some more questions, if any.
So thank you very much for sharing your knowledge about self-supervised learning. We have a few minutes left till 8 p.m. and we have a few questions already in the Q&A part. So the first question is from Carlos, and it's a longer text. With self-supervised learning, we are distorting our information by removing some parts of it. So I assume a bigger data set is required to achieve similar results in comparison to traditional supervised learning, which may also use regular data argumentation. Is that always the case? So we are trading the labeling efforts for a bigger data set. Any quantification possible about this trade-off?
Good question. Now, based on my knowledge, the trade-off doesn't exist. So you can simply, so while we are distorting, yes, we are sort of increasing our data set size here. So maybe like if you have one data set which has 10,000 images and you are transforming all of them using 5 augmentations, for instance, therefore 10,000 times 5, you will have a data set which has 50,000 images. And I guess the question would be like, does 10,000 times 5 compare to a supervised performance on 50,000, right? So if I understood correctly, and that is the question, my intuition would be self-supervised learning will perform better because it's not a rote task. In my personal opinion, supervised learning is a very rote task. You're just sort of throwing numbers at a network. It's not actually training something which is very rich in the representation space. And again, that is my opinion. I don't remember any numbers. However, I think the DINO paper does have something which is related to this particular question. So I would recommend going through that. Either the DINO V1 or the DINO V2 might have something which is along the lines of this particular question. Thank you, Carlos. Like that's a very good question. I would like to explore that as well.
Okay, I guess this was helpful, but Carlos, you can give us feedback in the chat. Next question. Can one apply these transforms on the MNIST dataset as a POC?
Yes, of course you can. In fact, if you go to my repository, you will see that I use Cypher10 and not MNIST. I'm not sure why. I think it's purely like I just randomly wrote Cypher10 instead of MNIST. But yeah, you can very simply apply these transformations to any data set. It is not a data set specific thing. You can apply all sorts of augmentations to smaller data sets as well. And in fact, that is, in my opinion, what you should do. So if you have a data set with fewer classes and fewer samples, you should apply a lot of augmentations, like apply 10 to 12 augmentations, create lots of views. However, if you have like a bigger data set, for instance, you should perhaps apply relatively fewer transforms because you already have like a feature-rich data set to begin with. But yes, answering that question, yes, it is possible to apply it to MNIST as well.
Okay. Then next question, it's a bit longer again. I read in the cookbook, page 4, our goal is to lower the barrier to entry into SSL research by laying the foundations and latest SSL results in the style of a cookbook. But it seems that all of this is very complicated. And now there's a question coming. What is the best YouTube video, in your opinion, that show this topic with a demo for newbies to understand what is going on in a different language that helps newbies what is and how this is used?
Wow, okay, I've never been asked to recommend a YouTube video. This is a very nice and fresh question. Thank you to whoever asked it. Okay, if you are a person who prefers sort of conversations, then I would recommend the Lex Friedman podcast with Ishan Misra. It's relatively longer, but then again, if podcasts is your thing, definitely listen to that. Yannick Kilcher has some YouTube videos on SimClar and DINO as well, I think. So definitely go through that. Code implementations. So I think if you simply Google SimClar implementation, there is some person out there who has written like a really nice implementation and made a corresponding YouTube video as well. Over this year, I will myself make some videos on self-supervised learning as well. So maybe check those out in the future as well. But yeah, so Ishan Misra podcast and then Yannick Kilcher's videos. Yeah, that would be the recommendation. And thank you for the fresh question. YouTube videos. Nice.
Okay, thank you. And then there's one last question. These methods are meant for restoration or contrast. Does it mean we cannot use them for other tasks like classification, object detection, etc.?
No, so you absolutely can. I think maybe I missed out about that during my talk. But what you essentially do is you treat self-supervised learning as a pre-training paradigm, right? So you use them to just get the weights. So for instance, if you do image classification, you will most often use ImageNet weights, right? The goal with self-supervised learning here is to use, for example, SimClar weights or SwAV weights. So once you have these pre-trained weights, you can put on like a smaller model on top of it, and then you can train them for various tasks. So for example, if you're used to the Hugging Face paradigm, right, you have auto models, and then you have auto model for sequence classification. You have auto model for named entity recognition, auto model for question answering, right? So that is what we're trying to do here. We're just trying to get like a general representation, and then you can put on very small models on top of this and train for whatever task you want to do. So you can have the same weights and then fine tune it for classification, for segmentation, for regression, or whatever.
Okay, nice. So this was the last question. And then I will come to the ending slide. I will check.
Yep. I will stop sharing. Okay, I have. Okay.
Yes, so thank you very much again. And if you want to get to know about more expert talks, then subscribe on YouTube, follow us on Meetup, join our next community talk, follow us on LinkedIn, and tell other Gen AI gurus. And then I can say thank you for being here. Thank you for asking questions. And Saurav, thank you very much for being here. And then it's 8 p.m. And I wish you all a wonderful rest evening.